Hi everyone, me and Anko will be presenting Railenium's work on the topic artificial intelligence for digital twins, focusing on some railway applications we have been working on. We will first give some explanation on the status of standardization of digital twins, on its definition and existing methodologies to develop a system twin. Then we will pass through the digital twin project best practice and the requirements. In the next section, we will expose the technical concepts of digital twin fed by automatic data processing in railway applications such as railway infrastructure, diagnostic, environment monitoring, and virtual testing. Finally, we conclude with some perspectives on the applications and challenges of the development of digital twin. To begin with, there are three main groups of work. The work of digital twins is based on the work of digital models and our interoperability standards, and each of these work groups are instrumental in the digital continuity of the assets, process, or system. The work on the standards provides a framework for normative interoperability for the other two groups of work, and this at the semantic, technical, organizational, and the legal levels. The work on digital models provides digital durability of the asset, process, or system at a given time, but also provides a foundation for the development of digital twin work. The work on digital twins offers an additional building block with its synchronization between the states of the real world asset, process, or system and its virtual representation. This is the key feature that distinguishes the digital twin from any other model digital representation. So, what is the definition of a digital twin? The digital twin is defined by the Digital Twin Consortium and the ISO 247 as being a virtual digital representation of a real physical entity. It can be a person, equipment, material, process, management, environment, projects, or supporting documents. May require in certain phases of a project synchronization at a specific frequency and fidelity. Also, we can quote Dr. Tully, who says that the digital twin aims to transform unstructured data into structured information around which develop services, allowing its exploitation. By this, we can find two approaches for the development of digital twins. The top-down approach, it's an approach that is mainly used if the digitalization of the project has started from the design or construction phase. There we will establish a very large multi-businesses or multi-domain digital model, which will then be used to produce one or more digital twins. Each digital twin will respond to a specific use case, which will determine the level of information need to be filtered from the digital model, and also which will determine the types of IoT and machine learning, allowing to create the link or the synchronization between the digital model and the physical entity. The second is the bottom-up approach. It's an approach that is mainly used if the digitalization of the project has only started from the operation and maintenance phase. Its objective is to respond to a specific use case and therefore optimize the development of the digital model and the dynamic data to be captured with the IoT and machine learning to make this synchronization between the digital model and the physical entity. And finally, work on both approaches is framed by a normative interoperability framework, which we'll look at later. So how can a digital twin project be successful? All that are the key points for a successful digital twin project. The better define the needs, objectives, issues, and the requirements of the project owner. First of all, we must define the use case we want to deal with. Then know that what level of digital twin we want to have, depending on the phase of the project and its objectives. Then refer to the ISO 247 standards as a checklist with contains the 50 requirements of digital twin to facilitate the collection of the project owner requirements. And finally, for the digital continuity of the project, we define the normative framework of interoperability on the semantic, technical, organizational, and legal level. So we will first see the choice of the use case. First of all, it's recommended to follow the ISO 247 standard to build your use case according to the template provided. But also it is recommended by the ISO 29481 standard to build a library of use case as you go along. The choice of the use case is naturally made according to the phase of the project, its digital continuity and objectives of the desired digital twin. In the design phase, for example, we can find the objective of optimizing design performance or to have a decision support platform. In the operation and maintenance phase, for example, there are several use cases with different objectives. We have maintenance and inspection, which can have the following objectives: fault detection and diagnostics, predictive maintenance, autonomous maintenance, etc. We also have passenger mobility, which can have the following objectives: passengers mobility in stations, passenger flow forecasting and management, etc. But we agree that each use case and each objective leads us to a more or less complex digital twin. we will now see the levels of maturity of the digital twin. Therefore, there are 4 levels of maturity of digital twin. First one, it's a static twin. It's a digital model of objects, non-geometrical or conceptual, not subject to data exchange. It's a statistic or intrinsic model, often used in the design phase or for simulation, calculation, and extraction of the static data. For the dynamic twin, it is a numerical model with an integration of the data acquired in real time. It must allow unidirectional exchanges of information between the digital twin and its real entity. It allows the extraction, observation, and exploitation of dynamic operating data for different purposes, such as predictive maintenance, etc. For the communicating twin, this is a digital model with integration of data acquired in real time, sensor, IoT, etc. More complex. It's more complex than the previous one because it must allow two-way exchanges of information between the digital twin and its real entity. It can ensure by this dynamic data link in real time and control algorithm an action of the digital twin on the physical entity and vice versa. And lastly, we have the interconnected twin. It is interconnection with interconnection of several digital models. It allows an exchange of information between the different digital twins. Its objective is to organize a connected operation, example set of infrastructures, works, etc. The ISO 23247 standard can be taken as a checklist of the digital of the 50 digital twin requirements before starting a digital twin project to frame the objectives. We can, for example, choose whether the digital twin must allow the simulation of the physical entity it represents, should describe the state of their physical entity, including personal, equipment, material, process, facility, environment, product, or supporting documents. Must contain a unique identification of the elements of its physical entity. Must allow visualization of the model or filtering of the data for different purposes. Must be extensible to new application or use case. Must collect data from sensors installed on or around the physical entity. Must be able to analyze the state of his physical entity. Must correctly describe the state of this physical entity, or must be synchronized using an appropriate method, either real time or delayed, etc. etc. And now we are going to talk about the normative framework. Normative framework for interoperability aims to ensure the digital continuity of our assets. It includes 4 levels of interoperability. Firstly, technical or technological interoperability, which concerns the choice of data exchange tools or software, the version and the exchange format defines. Second, organizational interoperability, which concern organization and the process to optimize exchange and resources. Third, legal interoperability, which aims for legal compliance of stakeholders with the legal framework, whether national or international law, and with the established contractual agreements, intellectual property, confidentiality, terms, and respect for exchange. And finally, semantic interoperability which is based for the other 3 levels. It covers the meaning of words, for example, glossary, data dictionary, definition of traits and their perimeters, concepts and their relationships, meaning of data, etc. After setting up all the full scope of digital twin project, we can enter the operational concepts of mixing physical world and digital data-driven one.
Thank you, Nasiba. So the purpose of developing a digital twin is to understand the past and present operations, make predictions, and ultimately support decision making in some form. And so usually, digital twins are used as simulations. That allows cost-effective simulation without having to have the hardware in place and not having to disturb the live operations. And to do that, we need a good model. And unfortunately, for most situations, models are hard to construct from first principles. So for most complex systems, we need some kind of data-driven approach to construct the digital twin. A lot of approaches use a combination of machine learning and partial explicit manual modeling to build the digital twin. And so the result we get, hopefully, it's a powerful digital object that can be used to optimize the physical world and improve operational performances. The DT, digital twin, is designed by gathering data and creating a model that represents the underlying object, so that we can test the model and determine how accurate it is and it might be. So that includes data collection from sensors that might sit on physical devices, and also includes data acquisition pipelines. Let's take the example of the railway tracks infrastructure twin. Today, infrastructure monitoring is done cost effectively when data acquisition systems are on board, so they are embedded on trains. They may include multi-sensorial systems composed of perception systems. We can find cameras and laser-based sensors, localization sensors such as odometry or gyroscopic sensors also, and also system state sensors such as pressure, temperature, energy consumption, and many more measurement instruments. Their goal is to collect and compress data from the frontal view of a train, for example, transmit data to a data processing unit, that's on the slide, the perception and the incident prevention unit, that will analyze and extract predictions upon the tracks, for example, such as defects on the railway tracks, analyze life cycle and aging time of infrastructure, components, and many more predictions outputs of machine learning models usually. On the other hand, the virtual twin can send some additional notifications through systems such as traffic management or supervision to a decision-making system that applies a physical response to the train. It can be a speed restriction, for example, or just sending a radio message to all the following trains, for example. Finally, to feed the digital twin, predictions of the decision-making module have to be checked and then compared to the previous states of a component before raising a maintenance planified task. Here's an example of a basic algorithmic architecture of a railway track's default detection based on image level predictions of ballast. So the anomalies here are the ballast holes and the rail's deformation detection. Collected images passes through several steps of pre-processing to be consistent with the training dataset. They are then processed by the feature extracting model, which are now often based on neural networks actually. And in a supervised algorithm for which each defaults are known and represented in the training dataset, the prediction step works on the extracted feature vector to classify the default regarding the training dataset and outputs some scores on each type of anomalies. The results can be visualized in these images. Railway tracks are segmented, for example, and we can see detections of level crossing gates and tracks that have actually a bounding box representing the detection. We'll also pass quickly through some videos of real-time embedded AI that produces detection of moving objects, such as pedestrians and animals, trajectory prediction, anomaly detection, obstacle predictions also, on a train rolling at 120 kilometers per hour. The processed detection and images are then sent to the automatic train operator that will take actions by braking the train or warning surrounding trains, for example. And the second video is the output of a prediction model trained on 3D data from a LiDAR sensor. It uses reflection intensity of materials of objects to extract and learn features specific to each element of the infrastructure, naming buildings, level crossing gates, for example, tunnels, tracks, catenaries, and other elements of the context, such as ground, vegetation, and others. Another application of digital twin in railways concerns driving tests, and especially braking systems tests that are very complex to organize and very expensive. Virtual testing can be simplified through driving simulations corresponding to the real train system by receiving real-time position, speed, acceleration, heading angle, and other information sent by the data acquisition system. The simulation realizes the real vehicle control, and the simulation vehicle runs in the virtual scene, so that the motion states between the physical device and the simulated train are synchronized and realize the basic functions of the real vehicle in the loop. However, there are still some challenges to solve on the test solution, such as testing cost issues, testing flexibility issues, and also a smooth advancement of the test system. In the future promotion of the digital twin railway, driving virtual environment test system, the use of open analog interfaces to control code-based traffic scenarios is a major challenge and also a trend in the future. As a global conclusion, so in addition to these few examples of application of digital twins, others applications driven by real-time data collected from sensors, these complex computer models of physical devices can reflect almost every aspect of items, procedures, or service in railways. More globally, many large companies have used digital twins to find problems and improve efficiency of their systems. It was found that the integration of digital twins and AI has significant effects in aerospace flight detection simulation, for example, failure warning, aircraft assembly, and even unmanned flights. In the virtual simulation test of automobile autonomous driving, it can save up to 80% of the time and cost, and the same road condition reduce the parameter scale of the actual vehicle dynamics model, for example, and greatly improves the test accuracy. In the intelligent manufacturing of production workshops, the establishment of a virtual workplace environment can provide timely fault warning, extend the service life of the equipment, and ensure the overall workshop operational safety. And the last example, in smart city traffic, the real road environment is simulated and traffic accidents are restored, so that the traffic situation is clear and efficient, and urban traffic management can be carried out quickly and accurately, actually. Finally, we look forward the future of digital twins and AI, hoping to provide a reference for future research in related fields. And nevertheless, there are still many challenges and work to be done to actualize the potential of the digital twin. Just to cite a few of them, still facing the difficulty of collecting data types, such as missing or wrong data. This will distort the results and conceal failures in this representation. For example, if a vibration sensor fails, the oscillation of a wind turbine will be ignored completely. Another example of a challenge is the establishment of algorithms and models that faces great challenges also. For example, when software written for different purposes is manually patched together, other error may occur. And for that, we believe that without standards and guidelines, it is difficult to validate the generated model's accurateness and representation of the physical device. To conclude, huge datasets and automatic processing by AI algorithms is one of the leaders and facilitators for growth and adaptability to enable digital twins target to the market and is becoming the main component of such systems. The open areas of research are evaluating the impact of AI, machine and deep learning algorithms, what they could potentially have on the progress and uses of digital twin technologies. And that's how Railenium believes that AI is actually paving the way for more case studies in an industry setting for evaluating the predictive maintenance and remaining a useful life of systems as a case study. Thank you for listening us, and we remain available if needed.